Hey guys, in this video we're going to continue on with the second question in the practice questions for the final. Okay. Um, in the previous video we just showed how every element of R mod I can be uniquely represented as a polynomial in X plus Y times a maybe different polynomial in X. Okay, where, let's just remember, X is the coset of big X. Y is the coset of big Y. Okay. And using this unique representation, and notice that the relationship between X and Y in R mod I is that X squared plus Y squared equals 1. So just in this I'll just put it up here. In R mod I, we have X squared plus little y squared equals 1. Okay. And now using this unique representation, we're going to show that R mod I is an integral domain. Okay. I didn't really want to just tell you to like assume this because we can certainly, it's like not too difficult to figure out that elements of R mod I can be represented uniquely like this. But I think it's safe that if you were writing this solution, it would be safe to say like we're going to assume that elements of R mod I can be represented uniquely in this form, and then go from there. So we need to show R mod I is an integral domain. So let's take A and B to be in R mod I. So we can write A as A0 polynomial in X plus A1 times Y, and B as B0 plus B1 times Y. Okay. So let's write them like this. And assume A times B equals 0. And our goal is to show that like A or B or maybe both are 0. Okay, so let's just multiply them out. Like this. Okay, multiply them out. You get A0, B0. You get A1, B0, Y. You get A0, B1, Y. And then you get A1, B1, Y squared. Okay. Now we know that every element in R mod I has a unique representation as polynomial in X plus Y times another polynomial in X. This has a Y squared, so let's get rid of the Y squared, remembering that X squared plus Y squared equals 1. Okay, so in other words, Y squared is 1 minus X squared. So A0, B0 plus 1 minus X squared, A1, B1. Oops. And then we have plus A1, B0 plus A0, B1 times Y. And now this is 0, so let's set it equal to 0. In other words, this is the expression 0 plus 0 times Y. Okay. Now, things have a unique representation as something plus something times Y, where this something is in terms of X. Okay, that means that this has to be 0, this is 0. Okay, now these are both expressions in one variable, so it makes it like a little bit easier to work with. So we have A0, B0 plus 1 minus X squared, A1, B1 equals 0. And we also have a1b0 plus a0b1 equals 0. Okay, so far so good. Well, this is just like linear algebra or something. Let's try and eliminate this. Okay, so to do that, we can multiply the first equation. Let's number these equations. This is going to be 1, it's going to be 2. Let's multiply 1 by a1, and let's multiply 2 by a0. Okay, let's see what happens. Well, we get a1, a0, b0 plus 1 minus x squared, a1 squared, b1. And then we get a0, a1, b0, same thing, plus a0 squared, b1 equals 0. And we subtract. Let's call this 3, call this 4. Let's do 4 minus 3. Okay, do that. What do you get? You get a0 squared b1 plus, or I guess I should say minus 1 minus x squared a1 squared b1. That's equals 0. Okay. And there's two possibilities. Okay, so, and then this is called this 5. And if you factor 5, you get a0 squared minus 1 minus x squared a1 squared times b1. That's equal to 0. Okay. So, these are all polynomial expressions in x, meaning that, so this is an equation in R of x. In other words, it's an equation in an integral domain. So either b1 equals 0 or this expression equals 0. So let's do both cases. Let's start with the easier one, that b1 equals 0. So this is an integral domain. Okay. So what happens if b1 equals 0? Well, let's just go through our equations that we have. If b1 equals 0, then we have a1 b0 equals 0. And we have a0 b0 equals 0. So let's substitute into 1 and 2. And what do we get? We get 1 says a0 b0 equals 0, and 2 says a1 b0 equals 0. Call this 1 prime, 2 prime. Why not? Well, if b0 is non-zero, then both a0 and a1 are 0. Okay, or b0 equals 0. So either b0 equals 0, in which case we're done. So b equals 0 plus 0, y equals 0. Or if b0 is non-zero, then again you have we're working in an integral domain, so a0 and a1 are both 0. So a is 0 plus 0y, which is 0. Okay, and so in this case we're done. Okay, so this was a quick case, right? The other case, so in this case, completely done. Well, what about the other case? The other case is that this other expression is 0, so a0 squared minus 1 minus x squared a1 squared equals 0. And we want to explain, we want to prove that both a1 and a0 are 0. Okay. Again, and now we're working completely with polynomials in X. So kind of, it makes it somewhat easier. Okay, this is supposed to be a 0, not like a delta or something. Okay, so let's just rewrite things. Okay, and we see that there's kind of like a problem. Here we have a square times something equals a square. So the something actually has to be a square. And you can kind of, this is kind of a similar problem to when you prove that the square root of 2 is rational. You know, you have, if you just, let me just briefly remind you, you write square root 2 equals p over q, and then you end up with an equation like 2q squared equals p squared. And so you have a 2 times a square equals another square, meaning that 2 is a square. And you kind of get problems for that. Like you say like 2 divides p squared. Well, if 2 divides p squared, then 2 divides p. Well, then 2 squared divides p squared, and then, you know, you go from there. So, and we can do something similar with this equation, remembering that a1 and a0 are just polynomials in X. Okay, so what does this mean? This means that a0 of -1, so we're substituting for x, a0 of -1 is just going to be 1 minus -1 squared times a1 of -1, well, that's just 0. Okay, so -1 is a root of a0. Similarly, a0 of 1 is 0. Okay, so 1 is a root of a0. Well, if a polynomial has -1 as a root, it has a factor of x plus 1. It has if it has 1 as a root, it has a factor of x minus 1. So x plus 1 and x minus 1 are both factors of a0. It turns out that means that 1 minus x squared has to be a factor of a0. Basically because these are coprime. Actually, don't want to worry about that too much. Sorry. Anyway, so we have 1 minus x squared is a factor of a0. Well, let's like, so we can write like, you know, we can write, let's say, alpha, oh, sorry. We can write a0 equals 1 minus x squared times another polynomial. Let's say, like c0. Okay. And now we replace a0 with 1 minus x squared times c0. And what happens? Well, on the left, we have 1 minus x squared times c0 squared equals 1 minus x squared times a1. Okay, and now we cancel. And now we have the same equation, except before we had a0 and a1, now we have c0 and a1. So again, we see that 1 minus x squared has to be a factor of, oh, sorry, this should be a squared. Right? So now 1 minus x squared has to be a factor of a1. So you substitute both sides and you cancel. Anyways, you can write, by the same argument, a1 of x is 1 minus x squared times c1. Then you get an equation like 1 minus, the same thing happens. Now this cancels with this. Okay. And you're back to where you started, except the degree of C1, right? The degree of C1 is 2 less than the degree of A1, and the degree of C0 is 2 less than the degree of A1. Okay? But the same argument tell you that you have to do this, that the same thing has to happen again. Okay? So, I'll just say this process continues indefinitely. But this can only happen if both A1 and A0 are 0, because the degree kind of goes down by 2 each step you take. Okay, meaning that, what do we mean? Well, if I have an equation like this and the degree of A0 is like 100 and the degree of A1 is 98, well, at the next step, the degree of the new equation will be like 98 and 96, and then at the next step it'll be like 96 and 94, and the argument keeps on going through no matter what. So eventually you'll get like degree 2 and degree 0, and then you'll get degree 0 and degree -2, and that's a contradiction, right? So the only way that works is if the thing you started where it was both 0, because then the degree is undefined, and this kind of stuff. Then this, if both sides are 0, then this argument is kind of like if you go through this argument, it says like 0 squared minus 1 minus x times 0 squared equals 0. So of course you can write 0 as 1 minus x squared times 0, and it's just like fine. Okay, so in this case we've shown this. So a equals 0. Okay, and now we've shown that if AB equals 0, then either B equals 0 or A equals 0. So now we conclude that R mod I is an integral domain. The end, except it's not the end of question 2, because question 2 has a bunch of parts to it, but that's the end of this part of question 2. Okay, thank you for watching.